Okay, welcome to class number 6, technically number 4 here, everyone. Glad to have you again for another insightful 3 hours of basic SQL. So let's go ahead and get started. So tonight, this is the same agenda that we've had for the majority of class. And tonight, we're going to be going through class number 4. Tonight, we're going to practice data joins and unions after we learned some of the basic join and union criteria and syntax in the last class. And then we're also going to talk about database modeling and entity relation diagrams, in addition to OLAP versus OLTP, OLAP, OLTP. There are some differences in this, but hopefully it'll all make sense when we talk about the course in the grand scheme of things. The idea here was that class 1, we would learn about some of the basics, how to ask a question, how to translate that into a SQL query. These are all things that a data analyst would typically do. Class 2, we talk a little bit more about operators and functions, case statements and logical operators and functions. These are things that data analysts and a data engineer will do from time to time, as well as a data scientist. Class 3, where we create databases and tables, prepare data, learn about joining data. These are all things that are very specific to a data engineering position. And then class 4, class 5 are going to be more in the data engineer and data architect land. So it's going to be, now that we know how to retrieve data out of a table, what that data stored in the table represents, now we're going to learn about how to organize it into what's called a data model. And there's multiple different ways of modeling data, as you'll see in the class today. And we'll cover multiple different ways of modeling data and demonstrating how data goes from one system all the way to even like an analytical processor like Power BI and Tableau. And then we'll talk about in class number 6 how all of this kind of loops together and talk about how we're going to do a basic project for the last assignment in the course. So some announcements. If you guys have a makeup assignment from class 1, just a reminder that those are due by Friday at midnight. If you need any help, I will be available after class and we can talk about any questions that you might have, or I'll hopefully help clarify some of the things that are on the homework if you're getting tripped up. And then we only have 2 more classes left. So what do we mean by bringing it all together for the final course? We're going to take elements from every single class that we've had so far, and we're going to create kind of a pseudo data science project. I guess I shouldn't say pseudo because it kind of is a real data science project. And one of your tasks is going to be to find a data set that you like. It can be one that you research on your own. It can be on a data, or it can be a data set from a website that we discussed, and I think it was class 2 or class 3. But the idea here is that you'll find a data set that contains some information that you either want to know or you already understand quite a bit of the subject. So hopefully it's something that you'll be able to use into the future, or with your newfound knowledge in SQL, be able to practice on and apply some of these concepts in a variety of ways, even after the class is over. We'll talk about how to find the data, how to import it, how to query it, and some of the things that you can learn on the data set with just some basic SQL techniques that we've learned over the last few courses. So what are we going to cover tonight? We're going to cover SQL joins again, what they are, what they're used for, how they can be useful, and we'll apply these on the tables that we have already ingested into the database. Over the weekend, I was able to get all of your guys's personal databases cleaned up. So now you have copies of the exact same tables that we'll be working with. And on top of that, we will practice these joins. Primarily, we'll use inner and left joins, and we'll go into that as well as a few other join techniques that are also available. We'll also learn about database modeling techniques, and then why we might use OLAP or OLTP database types, what those differences are, and the cases where they are practically used. But to start out, we're going to go ahead and take the quiz. So this quiz is going to cover a lot of the elements that we covered in the previous courses. I'm going to send this in our Slack channel here, and I'm going to give you guys 10 to 15 minutes to complete this. I think we'll probably go 15. I don't think you'll need all of that, but when you guys are all done, or when you are completed with the quiz, just go ahead and post a comment here in the StreamYard chat, just letting me know that we're done. And then when everyone's done, we'll continue on to the rest of the class. Sound good? All right. Good luck, everyone. We have one more quiz yet to be submitted, so hold on for just 1 second, and then we will go over the answers, and I'll take any questions on the quiz that you guys might have had, and then we'll get right into class. Never mind. Everyone is submitted, so we should be good to proceed. So let's talk about this quiz. First name or first question, what is your name? Hopefully everyone got that one correct. Looked like everyone did, so that's good. Second question. So what kind of key constraint uniquely identifies each record in a table? This would be the primary key. The primary key is what identifies what makes something unique. What defines the table? How does the table operate? That's what the primary key is here to do. And then the foreign key is the key constraint that identifies the common relationship between two tables. We'll talk tonight about how foreign keys are really similar to joins and how they behave. Because when you join one table to another, you could reference a primary key, foreign key relationship. But this foreign key relationship is going to be what identifies that relationship between the two tables. We can set this up in our create table statement. So this would be an example of when that would be used. Question 4, if you were working with a customer table and wanted to add a new column, what kind of SQL statement would you use to do that? You'd use the alter table statement. When you use that alter table statement, you'll define what table you want to alter. In this case, it would be something along the lines of alter table customer, and then you would add add a column with whatever name you wanted to call it. Question 5, true or false, database tables can be renamed without impacting other applications or database procedures. This is false. The reason that it is false is that even though it's relatively easy to rename a table, the downstream effects are that anything that a developer or a programmer has developed on top of the data tables that we reference would then have to be changed so that it would reflect the new name of the table. So it is very important when we talk about altering tables, altering columns, dropping tables, dropping columns, that anything that references it on the application side, or even in a view or a procedure on the database, is changed to reflect that new name that you've given either the table or the column, or that job, that operation will fail until it's repaired. And then question 6, what are some reasons the SQL joins are useful? They improve database and query performance. They enable for more complex analysis, allows us to spot trends easier, aggregate by values that aren't stored on our base table that we're attempting to measure. And they also eliminate the need to restore redundant columns or data. So this is data that might appear over and over and over again, but have what's called low cardinality. That means that there's very few possible options for a value to correspond to. So think about maybe colors, for instance. If we were looking at a sales table and we were looking at all of the products that have been sold to our customers, we might want to have a column that describes the color of the product that was sold. But the thing is those sales tables or the transaction tables can grow to a really large volume. And so when we store that value, it takes up a lot of space, when in reality, we may only have 4 or 5 different colors of product. So it would be easier to have a column for that order corresponding to a product table. And that product table could then store the color of each product on the row. So there's a lot of reasons why SQL joins are useful, but in this case, all of the above answers were correct. So everyone was able to submit the quiz, so we will go ahead into the lecture. Are there any questions on the quiz or questions on the answers? All right. So let's talk about how joins work again. There's 4 types of joins that we're going to use, and the most frequent joins that we'll use in data analysis, especially basic data analysis, are going to be the inner join and the left join. Optionally, you can call it the left outer join because that is what it's doing. The other join types that we may use for very specific use cases, although not much in basic data science, business intelligence, basic data analysis, are going to be right join and the full outer join. However, there are cases that these will be used. But the 2 primary joins that we're going to practice tonight are the inner and the left join. So what does the inner join do? It shows the columns and values from your base table that you're querying. So think about a sales table, and it's only going to show the records from a joined table that have a match. So a question that you might be asked for this particular scenario is, I want to know how much revenue we've accrued on all of our sales, regardless of if we know who the customer is, or only if we know the customer. Sorry, this is the inner join. So the inner join would be, I want to know all sales for customers who have a matching sale or a matching customer record. And then the left outer join is going to show columns and values from your base table with the columns and values from the join table, regardless of if there's a joinable record. So think about if you were asked to return the revenue from all of your sales on a sales table, regardless of if they have a customer record. You may not be able to aggregate by things like customer demographic or where the customer lives, but it is a sale, so we have to record it as revenue. And in a lot of cases, even if we don't know who the customer was or we don't have further information about the customer, the sale in and of itself is valuable to us in determining how much money we made in the previous year, and maybe even how much expense was accrued facilitating each of those orders. The right join is going to be kind of similar to the left join. However, you're only going to show values that have a match on your join table, and any records that don't have a record or don't have a value or corresponding value on your left table, which is your base table. And then the full outer join is going to return all of your values. So regardless of if there is a match on either side of the table. So let's talk about what this looks like with a real data set, because I can only sit here and tell you about some questions that you might be asked, but how does this look like in the back end from a table perspective, right? Data analysis is all tables storing rows and columns. When we look at a left join, let's think about our A table as being our customers table. We might have information about who the customer was, where the customer lives. When we talk about maybe changing dimensionality, so like a customer may not live in the same location for a long period of time, but what happens if they move? We have the option of updating their address on file, or we could retire their old record, keep all of the references to a sale, and then insert a new record for their new address, and then affiliate all of their sales going forward with the new address. That would appropriately apply address changes, and we can further understand where our customers are buying their product instead of where are our products or where were our products sold based on our customer's current location. There's a big difference between the answers that you could receive in each of those different questions. So in this case, let's talk about how this table join works. We're going to select everything from our customers table, and we want to see how much our customers have spent on any of our orders, our table B. When we do the left join, what we're telling the SQL query engine is, I want to see everything in my customer table or the table that I select from. And then if they have any sale records, I want to return some information on each of those sales records for the customer. In this case, we have sale records for customer ID 3 and 5, but we don't have information, or we don't have orders for customer IDs 1, 2, and 4, John, Robert, and another John. So what happens here in the table is we return all the customer IDs, and it looks like this query was probably indexed, so it's ordered by the customer ID. We return any of the information we want from that base table, And then we return the join or the data that has a valid join from that orders table or the table B. And in this case, since we have a 500 and an 800 for David and Betty, that's what gets returned. But if we have multiple orders and we joined on this same criteria, we could actually run a sum where we say return or select the customer ID and the first name, and then sum every order that they've ever bought. Because we might have multiple records, or the customer might have multiple orders from the same store. But if we want to know how much they've spent on every product they've ever purchased from us, this is a chance where after we join, we could actually aggregate everything based on a joined table. So when might we use a left join? A good example is when we know which tables have a relationship, but the data in the tables haven't been validated, or you don't know if there's a match in the other table, or if you did, and the use case was specific enough to warrant using the left join. So when I talk about like data mining, for instance, when a lot of companies start their data science department, or they start getting into exploring the trends in their company's data, they might have to just query every single table that's on a database to start to even understand what the data represents. Are there corresponding tables that might give us more information on the things we want to measure? That'd be the case where it's easy to use a left join, because even if there isn't a valid record on the other table, you'll still return everything in your measurable table. And then if there's a row that describes what happened on your base table, you'll return any of those attributes. So there are a lot of cases where you might want to only return records that have a match. And that's the case where you would want to use an inner join. So the inner join is used when we know that tables have a relationship, or we want to suppress any rows that don't have a match in the other table. So in this case, we'll use the same customers and orders table. And when we look at this, the question that was most likely asked is, I want to see orders for our customers where we have a customer record on file. And in this case, since our orders table only has order ID or orders for customers 3 and 5, which are David and Betty, we're only going to return their order quantities from the order tables. We're going to exclude customers 1, 2, and 4, and we're not going to return any information on orders 1, 3, and 5. Common cases or common questions that you might ask when you perform an inner join might be on things like a data warehouse, where a lot of this data has been vetted and validated, or we know that there's going to be a match on this joined table for every record. And in a lot of applications are developed to have codependencies. So some tables will require properties to be stored on another table when we get up to scale. And an inner join is effectively going to remove duplicates if there are any, and you'll only return records with matches. So these are the two join techniques that you'll use most of the time, and they'll solve probably 99% of the use cases that joins are used for. So it's helpful to really remember the differences between a left join and an inner join. Does anyone have any questions on left join or inner join before we go forward? All right. One thing I also want to discuss in this class are some common syntax errors. I'm sure you've written a query in MySQL Server, and it takes a little bit to think about what may have gone wrong. But some of the most common things that we see when we query are that there could be a spelling error. You might name a table wrong. You might define a column incorrectly. You might have an invalid value spelled out in a comparison function. So thinking about when you want to filter out data from a different year, like in our calendar table, maybe you just say where the year is less than or equal to 2023, and you miss an A in year. That would cause your query to fail. And so that would be an example of a spelling error that you might encounter. We also have quotes. So there is a difference between using single and double quotes. I recommend using single quotes in most scenarios. However, the double quotes will actually get around some issues that you might run into when you have a single quote. So an example of this might be when you have a string value in a column that has an apostrophe in it. So think about if we try to store like a comment on like a Facebook post, you might have I'm trying to think of the word. This is why I'm a computer science guy, not an English major. But when you put two words together, you use an apostrophe to essentially eliminate the letter that's not used. So like have and not would be have int. When you store that apostrophe, if you use a single quote, it's going to treat that apostrophe like the end of the string, and that could cause the rest of your query to fail. So that'd be an example of a time where you'd want to use a double quote in your select statement or in your SQL query. Another issue that you may run into is the order of your SQL clause. So in the first class, when we talked about how to formulate a basic SQL query, the most important part that you want to remember is select star from table. But what about some of the other clauses that we can add on to that or tack onto it? After you select everything from your table, you may want to, or you may add an aggregate into your select statement. That requires you to have the group by. And then if you want to order by another value, you have to put the order by after your group by clause, because when the query engine is thinking about how to execute your query, it's taking all of these columns, aggregating it based on the value that you've chosen, and then it's grouping it by the aggregated attributes. Then you can order it by whatever value you want. When the order by and the group by are in the incorrect order, your SQL statement will fail. So it's important to understand how a SQL clause is ordered and continue to follow that as you write out more queries in your time in SQL. Another error is that you might join on the wrong column, and this frequently happens all the time, especially in data analysis and data mining. You may try to join tables that you are not familiar with. And when you join on a column, if there's no match or the column name's not right, your query will return no results. And so if you were expecting it or you're still trying to figure out what the right relationship is, you might just change the column name several times until you get it. And sometimes you might have a spelling error in that column definition. So it's important to make sure that we also join on the right column. And then the last thing is you may overfilter data. This isn't as applicable to the things that we've learned today or in the last few classes. But what we mean by overfiltering data is based on the query that you create, you may use a logical operator like a less than, a greater than, or an equal to, and it may filter out more results than you're anticipating. So make sure that you use those logical operators in a way that's applicable to your particular scenario. And then I do have a little bit of a reference guide that you guys can look at on datapractices.org that I'm going to link in our Slack channel during our next break. But it will go over a lot of these syntax errors, and it'll talk about how to formulate a SQL query and a lot of things that we've talked about already. So it's good as a reminder to review some of this information as we go forward. So next, let's talk about how we can practice inner and left joins. So everyone should have the same data in their databases now. You'll have a biking table, a toy sales data or table, a Netflix titles table, and then a calendar and a US zips table. And we're going to practice the left joins and the inner joins on each of these tables. You can see in the descriptions that biking will show all of our bike rides that we've taken by date. Toy sales contains sale records by date, and we also have customer zip codes. And we have Netflix titles, which are movies and TV shows based on the date that they were either released or published to Netflix. And sometimes what these tables are called, we're going to use them as our base tables. So think about how on our left join, we had table A, table B, and then our inner join, we had table A and table B. These fact tables are going to be used as our base tables. And we'll talk about what a fact table and a dimension table are later on in the class. But these base tables are going to be what contain the things we might want to measure or the things we might want to aggregate on. And then our dimension tables will, calendar will have every date with quarter and month attribution, and then US zip codes will have some information on each of the zip codes that we have on file. And then some basic syntax. When we formulate a join, the first thing we need to do is create the actual query itself that we want to measure. So this would be something like select star from the biking table. And then if we know what table we want to join on, this is where we start to use either the left, the inner, or even a full outer join if warranted. If we wanted to return all of our bike rides, regardless of if it had a valid date, we'd want to use a left join. If we wanted to only return bike rides that occurred during or that occurred during a date we have in our calendar table, that'd be an example of when we would use an inner join. Or if we wanted to talk about toy sales, that's another good example. If we wanted to return all of our sales, regardless of if they had a valid zip code, we would want to use the left join. And then if we only wanted to return sales that had a valid zip code, that'd be when we use an inner join. When you join, you'll do the inner or the left join, and then define the table that you want to join to. So in this case, our table 1 is either going to be biking, toy sales, or Netflix titles. And then our table 2, in this case, is going to be calendar or US zips. And these are considered our dimension tables. And when we declare what table we want to join to our base table, we have to declare what criteria we join it on. So you'll use on, and then whatever the joined column on the first table is equal to the column on the second table. So if we actually go back to the examples back here, I think this one's a good one. So if we wanted to join or left join the customers and this order table, we would select star from the customers table. We call that table 1, T1, A. You can alias it, whatever you'd like. And then our table 2 would be our orders table. So it would look like select star from customers, table 1. And then if we wanted to do a left join, on the next line, we would do left join the orders table, and then call it B, call it table 2, or whatever we want, on, and then the exact relationship criteria for the columns. So in this case, our on criteria would be table 1, which is customers, dot customer ID is our first column that we want to establish, equals for our second table, T2, table B, whatever you called it there, dot customer. So if we wanted to write this out, we'll use some examples, but that would be how we'd formulate the left join. If we did the inner join, it'd be relatively similar, except instead of left, we would use inner for our join. So select any of the columns you want from table 1, any of the columns you want from table 2. If you want all the columns from one table and then only columns from another table, you can do T1.star, which means return all of the columns from the first table. And you can define even some of the columns that you want from the second table by going T2.column1, T2.column2, so on and so forth. And if you just want to return everything from both tables, you can just do select star. You don't have to name, or you don't have to define any of the table prefixes in that select statement. One thing I will touch on for aliasing, you see this T1 and the T2 here in the syntax and how we declare it throughout the query. This is one thing that is important to know about SQL joins in particular. You do need to alias each of these database objects, whether it's the column, the table itself, or the join criteria. And these aliases can get kind of long. In a lot of use cases, I've worked with tables that have extremely long names or they're very specific to a particular measurable. And it might just be easier to write the code as like T1 or table 1 or even like A, B, C, D, depending on how many tables you end up joining. The more complex that your queries become, the harder that it can be for anyone down the road to start to dissect. So when you write your queries, my recommendation is to make them simple, but not so simple that it's difficult to read down the table. Because if you have, say, 5 to 10 different tables that you're joining together to do a really large multi-dimensional query or multi-dimensional model, it can be tough to look at your select statement with all of your columns that you're pulling out of the multiple tables and then try to figure out what T1 corresponds to, and then what T6 corresponds to, and then what T5 corresponds to, because it can be chained together and not necessarily all corresponding to the same table. So it's a lot easier to name it something that makes sense for the subject area that you're handling. So in the case of like biking, we might want to select star from the biking table and then name it rides, or even just biking. We maybe don't have to alias that. But if we were to analyze like sales, for instance, we might not want to call the table toy sales. We might just want to call it sales or orders or transactions, something that's easy to refer to, and you know exactly what it's pointing to as the developer. So to practice, let's open up my SQL Workbench and connect to your database. And then once we're there, we have a few different joins that we need to practice. We need to practice an inner join, and we need to practice a left join. So just to remind ourselves what an inner join does, the inner join is only going to return rows from tables, or only going to return rows that have a valid matching criteria or valid matching criteria. And the left join is going to return all rows from the base table and information from the joined table with a valid match. So an example of when we might want to use an inner join could be, let's go example, return all bike rides, or count, how about let's do this. Count all bike rides, which is going to be the biking table, that occurred by year. So what we want to do is we want to know how many rides were taken in this case should be 2021, 2022, and partial 2023. So the first step that we want to take is we need to query our base table or our fact table. What contains the thing we want to measure? And in this case, it's the biking table. So we'll write out our basic query, select star from learn_smcquiston.biking. And for each of you, it'll be whatever your private database is. You could query from the learn database if you like, since everyone should have select. Actually, how about let's do that. Since everyone can read from that learn database, we'll just do this so that everyone has the same code and they can copy. So we'll select everything from our biking table and run this query. Can we get all of our ride numbers, the dates that they occurred on, how long we went for the ride, how many minutes we rode for, and then what our average miles per hour was. So if we wanted to return information by year or like a calendar aggregation, this is where we would join the calendar table. So I'm going to alias our biking table as T1 just for simplicity's sake right now. And then if I only wanted to return rides that occurred during a date number or during a defined date in our calendar table, which I know we do because every column in this table contains a date, I could use an inner join. So in this case, let's use the inner join. we'll do an inner join on the table that we want to join. In this case, it's going to be learn.calendar, and this is our join table, T2. After we do this inner join line, now we have to define what allows this join to happen or to occur. And so this is where we create our logical statement, our on column. On what columns does this match work? If you don't know, you can always create another query to select all from our calendar table. But since we know what the column is on our base table or our measurable table, I'm going to write down the relationship for the first column, which is t1.date. That's the column that we want to join on. And then equal to t2, whatever that column is. And let's say I don't know what column that is. I'll go and run the select statement from the calendar table. And the date value on that calendar table is also labeled date. So we'll write the column for the join criteria here as t2.date. And when we do that, let's run the query and we'll see what we get returned. So if you remember, we had the learn.calendar and the learn.biking tables. And when we look at just the biking tables, the only thing that gets returned is the ride number, the date, the distance, the time in minutes, and then the average miles per hour. But when we join this table and we select all the records from the table with the star, we run it, and you'll notice that now we have all the information from our calendar table too. So instead of just having our ride number, our date, our distance, our time in minutes, and our average miles per hour, we also have the date or the key from the calendar table. We have the day of the year that it occurred on, the month number that this ride corresponded to, and the year and even the quarter. So now that we've learned how to do the inner join and we know what or how to write an inner join statement, what are some ways that we can use these joins to create some insights? One of the most practical methods of doing so is by using an aggregate function. And so let's say I wanted to know how many miles I rode in each month of last year. How might I do that? Well, if I want to return the count of rides, I would need to do a count star. That's going to count all of the rows that are in the table. And since I know that each row corresponds to a ride, and the ride number is our primary key on the table, I can safely do the count star because I shouldn't have any duplicates on my joins table that might result in multiple rows. That'd be an example of a many-to-many relationship where many records on the base table could correspond to many records on the join table, which we'll talk about a bit later. But for this example, we're going to count star because we want to know how many rides we took. And then how do we define what month and what year these rides occurred on? The other attributes that we want to add on are things from our calendar table. So count all of our rides and then group those by our month. And we'll also return the year. So t2.month and t2.year. And now that we have this, the next thing that we need to add, since we're counting or we're applying an aggregate in our SQL query, we have to group this data. So the next thing we write is group by any of the columns that we're selecting not wrapped in the aggregate function. So in this case, it would be t2.month and t2.year because we're counting all of our rides based on the year that it occurred and the month that it occurred. And why are we adding these two? Why don't we just return the month column? Well, there may only be one month every year in this table, but since we store month as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then repeat that every year, if we only group this by month, we would actually aggregate or count all the rows based on its month of the year and not necessarily the month and the year. So when we return the month and the year, it only counts the values that match that month and that year value. So 5 of 2021 doesn't get matched up in 5 of 2022. So let's run, now that we've grouped this query, there might be something else that could be valuable in our results. We might want to order this by the year, most importantly, because that's our highest level of ordering in this particular case. So we group it by year in descending order so that we show the latest year at the very top. And then, so in this case, it would be 2023 and then 2022 records and 2021 records. And then we might also add on T2.month so that we show everything in descending order from 2023 to 2021. And then for each of those year portions, we order it from December to January. So 12, 11, 10, 9, 8. And we'll put both of these in descending order. So now that we've written this, the report that we're going to generate is going to be the number of bike rides that were taken in this data set, grouped by the month and the year that they occurred. And then we want to order it so that we see the most recent records at the top of the report and the oldest records at the bottom of the report. So when I run this, you can see that we had 2 rides in March 2023 that actually increased to 3 as of yesterday. Took a nice birthday ride, got 30 miles south of Denver, and had a beautiful scenery. I just haven't inserted this into the database, so you just have to take my word for it. And then in February, I took 1 ride when it wasn't snowing. And then the last ride that I took at the end of the year in 2022 shows up here. But what if we expanded this? What if we wanted to really analyze and dig in how often we ride and when we ride the most? We can look at December of 2022. We only had 1 ride. It was probably cold. So the last thing I want to do is to have frostbitten face. And then in November had 5 rides. October had 9. So you can see the further back that we get into some of the warmer months, that's when the number of rides occur. And from this, we can even say things like, oh, well, in September, this data set shows that there were 11 bike rides that occurred. And since we know that there's 30 days in September, we can conclude that I took a bike ride once every 3 days on average. And then we can look at even some others and see how even the year over year has changed. If I look at 9/22 and wanted to compare how many rides I took in 9/20/21, this would be an example of how you could generate the data set to show it. And we can see that in 2022 September, I took 11 rides, and in September of 2021, I took 10 rides. So I increased the amount of rides I did in the month of September year over year by 1. So this would be an example of joining the data together and then applying an aggregate to understand maybe something that would be a little bit more tricky to figure out on the base table. Because if we didn't join this table, let's look at what it would look like if we wanted to count the number of rides we had on the biking table without using a join. If we look at what this biking table looks like, we have all the ride numbers. So we could still use the count star to return all of our records on that table. But the only date column that we have here is our actual date, which contains the year, it contains the month, and it contains the date. So what we could do is we could theoretically add a function on here and say, well, now since in my previous query, I have month and by year, I could do the month of date and use the month function. And then I could also use the year of the date to grab the year. And I'll alias these as month and as year. And when I group by, I would have to group it by the month. Yeah, the month of date and the year of date, and then order by the year of date and the month of date. And when I run this, I should get exactly the same answer. So this is an example of how there might be multiple ways of doing something, but it's generally easier when you have tables that are larger than like a calendar table, for instance, to just use the join criteria. So kind of similar to what we had talked about a few classes ago about there not being one singular right answer to get to what you're trying to answer for the requester. But there are ways that you can work smarter and use some of these tables to your advantage. Because ultimately, the more tables that we add, the more complex our data model becomes and the more questions that we can answer. And so long as the join criteria between these columns is valid for the rows that we want to analyze, we can pull in any of the corresponding attributes from those other tables and run this same kind of analysis on maybe not 130 rows, 200 rows, 1,000 rows, but millions, billions, tens of billions of rows, depending on where you work and what kind of data you analyze. And so the joins become that much more important over time, the more data you add to your data model.
Sam, I had a question.
Questions on inner join. We'll talk about left join next.
Sam, I had a question.
Sure.
Where you have group by T2 dot month, I guess all that in the order. Why does the order by start with T2 dot year instead of T2 dot month? I guess why are they flipped? I guess for order by and also group by. I guess I just want to make sure I understand that.
So the group by, you can put them in whatever order you want. You could put year first, you could put month first. This part, the ordering does not matter for the columns. This part for the order by is going to determine how your data is returned. So if let's say I don't put a descending on either of these, it's just going to order it by the year and the month. If we don't define what that order is, it could be returned out of order. And in this case, it looks like it's going in ascending order. But there's going to be times where you work with data that doesn't have a primary key, foreign key relationship set up, or there's not an index on that table, and it doesn't know how to sort the data that you have. And so when we evaluate the query or the data that we return, we might want to order it in a way that makes sense to like a business stakeholder, right? And so in this case, since we're grouping all of our data by the month and the year that it occurred, we have to order it in a way that makes sense. So if we ordered it by month in ascending order and then maybe year in descending order, that means that we start with that means that we would start with, actually here, sorry, maybe not a good response to your question, but the group bys, the ordering for the columns doesn't matter. The order bys will determine how your data is sorted. So if we put month here before the year, then it would return everything in month, ascending or descending order, and then the year. So if we have multiple months, say like we have rides in May of 2021, 2022, and 2023, it would return May 2021, and then May 2022, and then May 2023. And then it would start with the next row as June 2021, June 2022, June 2023. So to show you, let's actually run this query in ascending order. So right now, what we're showing is the year in ascending and then the month in ascending. So we start from the first year and the first months all the way up to the last year and the last months. So if we order this by month ascending and then year ascending, we're going to start with 1 if we had rides in January, of course, and then whatever that first year was. So I'll run this to show you. We start with 1 2022, and we have 2 rides. And then we have 2 of 2023, because that's February, since we ordered it in month ascending. And then we have multiple records for the month, because we we had bike rides in March of 2022 and March of 2023. But since our SQL statement is saying, I want you to order this by the month first in ascending order, it's going to take that month column and then return each of your rows based on that month value. And then it will look at your secondary value that you order by. In this case, it would be the year. And it would start to spit out those records in alphabetical order or ascending order again. So that's why for these 2 rows, you see 2022 first, and then you see 2023. But the example that we wanted is we want to see the most recent months first and then the latest months last. So that's why we have T2.year, because need to see everything from 2023 to then 2022 to then 2021. And we order that in descending order. And then we order it by the month, because we want to see, like right now we're in March, right? So we would want to see March of 2023, and then we would want to see February of 2023, January of 2023, and then loop back around to 2022 and see December, November, October. And to show you that again, after we run this, you'll see we go 3 of 2023, 2 of 2023. We didn't have anything in January of 2023. So we go back to 12 of 2022, 11 of 2022, all the way down, looping around. Does that make sense?
I'll have to rewatch this video again. Sorry.
Okay. All right. Any other questions that I can answer right now? All right. So let's talk about a left join. So we're going to shift context a little bit from the biking table, and we're actually going to look at the toy sales table. So the first thing that we want to do is select everything from our toy sales. So learn.toysales. And we're going to return this table and everything in it. So we have an order number, a quantity, a unit sale price, everything all the way over here. And then we have order dates, and we should have a zip code. So you see how some customers, we don't necessarily know what zip code they ordered from. We maybe only know the city and the state. But what happens if we want to see how many orders were placed on or in zip codes that were in California? Like, let's say we didn't have this customer state column here, and we only had the zip code, and we want to count, or we're going to sum. We want to sum the total sale amounts that we had in each of these zip codes. First, we want to outline our problem here, or our problem statement. We want to query all sales and their, let's see, we'll call it their state, based on the zip code for the order. First thing we know is that we want to query from our sales table, and the second table that we want to join is going to be our calendar table. So, or not our calendar table, sorry. Our US zips table is the table that we want to use here. And since we want to query it by the state, I need to know what that column is and what column we're going to be able to join on. So the next thing that we'll do is we'll create our join criteria. In this case, we want to use left because we know that we want to return all sales, regardless of if they have a zip code. But we want to know how many sales are occurring on or are occurring that don't have a valid customer zip code, for instance. So this would be the case where we would want to use a left join. So we would left join our US zips table. And I'm going to now alias these tables because I totally forgot. So I'm going to alias the toy sales table as sales. And I'm going to alias the US zips table as location. And now we need to establish what the join criteria is. So the next thing we need to write is on, and then the column that equals the column on the second table. And in this case, our table 1 for toy sales, if I forgot, which I totally did, I'm going to query the toy sales table again, figure out what that column is. So that column is going to be on sales dot customer zip code, and that is equal to our location table dot, I think it's just zip. Yep, it's just zip. So location dot zip. And so when I query this, just as is, we're going to return every order. And if the zip code has a matching record in the zips table, you'll see that we now have all the information about that particular zip code from our zips table. So it looks like most of the records that we get returned are in New York. But we also have some in Iowa, some in North Dakota, some in Louisiana, some in California. And so this would be the time where we can start to use some of the information from our sales table and analyze it based on the attribution or the join that we get from our zip code table. So let's.
So I understand, how you wrote the query. I guess my question is just, when do you determine that this will be a left join? If you could just explain that again, how you knew, okay, I'm going to do a left join, so that I can pull all of this information.
So the differences between those two, I guess a good example that we kind of covered just recently was you would want to use an inner join if you knew that every row that you wanted to aggregate or query on your base table had a matching record on that joined table. Or if you only wanted to query records on your base table that had a row that could be joined to. You might want to exclude information that doesn't have a corresponding record on that other table. And in that case, you would still want to use the inner join. But let's say you wanted to query everything from your base table, regardless of if it had a match or not, but you also want to return information about that matching record on the other table. That's when you would want to use a left join. The left join would return the data on your base table. So in these cases, it would be like the biking table or the toy sales table, and then whatever you wanted on that base table. So in the case of biking, we wanted to count all the records. In the case of toy sales, we might want to sum all of our sales that have ever happened. But let's say we looked at like the toy sales for the left join, for instance. Maybe I want to return the sum of all of our sales, regardless of if the customer zip code had a match on our zips table. That would be when we use the left join so that we still sum all of our sales amounts. But when we return the data, if there's information that doesn't have a match, it's going to show up as a null value. And that's our indication to know that there's probably a data quality problem. There may not be a record on the other table that it will correspond to. And in that case, it's because we don't have the information in our database to be able to query that. So there are going to be instances where these two can be interchanged, but it all depends on things like data quality. It depends on the format of the values. Sometimes a join will fail if you're not joining columns that are of the same data type. But there's multiple different ways of essentially figuring out what type of join to use. My recommendation is always start with a left join, because that's going to at least tell you if you have an invalid join relationship established. And then if you know that you're going to have a match for every record in your table, that's when you're okay with using an inner join. And the inner join is going to be a little bit more performant, but it's also going to remove those records that don't have the match. Did that make a little bit more sense?
Yes, it did. And then I just also wanted to ask you, just kind of as someone who is, getting my feet wet with SQL, did you sometimes just kind of play with them all, like inner join, left join, right join, just kind of see what the data pulled back to determine like what it is that you needed? Like, is that normal?
It is very normal. And to be frank, I think I have created more queries that have failed than queries that have succeeded.
Okay.
And that's just because of the research element to a lot of this.
Yeah.
I've come into companies where almost nothing was known about the data model, or like the semantics of some of the rows were relatively unknown. And as someone who has the skills for SQL, like how to create a query, how to identify rows that don't have a match, how to count the number of rows that have a match versus count the rows that don't have a match. That's what allows you to kind of elaborate on the data model and determine if what you've created is accurate or not, or if it's a good relationship to continue to use. There's a ton of different things that you can do to like quantify that. And so that's why I always advise using the left join right out of the box, because regardless of if there's a match or not, you'll return everything in your base row. And then if you do get some matches, you'll start to see those show up at the very end of the table when you query everything. So yes, it is okay to make as many queries as you want. And in fact, I would encourage that because you technically have an infinite amount of compute that you can run on this. It's just the amount of time that you're willing to wait for a result. But to answer your question, yes, there's going to be times where, especially when you're fresh or you're trying to understand the data model, that you just need to query everything.
Yeah.
You need to dive in, look at the records, and then think about what's common between all of these different tables. And it's not necessarily intuitive to do in like MySQL, but in other platforms like Microsoft SQL Server and Oracle, they allow you to run and display the results of multiple queries at a time. So that makes it a lot easier to like let's say we knew that there was probably a relationship between these two tables, the toy sales and the US zips table. What I'd be able to do in those programs is write out both of those queries and then run them all together. And then you would see two different query results pop up. And then you can explore the schemas of each of them, see samples of the data, and then start to write out your join statement above, which is where you would do like this left join. You'd say, okay, well, table 1 is at the top, table 2 is at the bottom. So table 1's column that matches is this, table 2's column that matches is this, and then continue to create more of those metrics over time.
Okay, thank you.
Sorry, did we have another question? I wasn't sure. I didn't see if anyone was talking. All right, guess not. So we'll continue, and we're almost done. So we will take a break here in about 5 or 10 minutes. But back to the left join. So when we're looking at this left join, let's say we wanted to return our total sales amount. That total sales amount is going to be a sum function. So I'm going to sum, and then I know what the exact column is that I want to sum on. So this is where you would declare it. In your sum, I'm going to put from that sales table, since we prefixed our toy sales, sales dot sale amount. And what this is going to do is it's going to add up all of our sales that have ever taken place. And then I'll name it as total sales. And then if we wanted to group this based on the zip code that these occurred on, like let's look at the learn.us zips, or I guess we could look at the product of this joined table on the right. Maybe we wanted to join, or maybe we wanted to sum our total sales by, let's even group it by we'll just group it by the state ID. How does that sound? So we'll do location.state ID. And I think that's probably good for now. So we'll order this we're going to order this by the sale amount because I want to see, or no, sorry, we need to group it first. And this is another thing. When you create these SQL queries, you will almost always at the beginning forget your group by. So the more we hammer it, the more we'll remember. But we want to group this by our location.state ID. And then we'll order this by our sum sales amount. Because we want to see the locations that have the highest sale amount all the way to the bottom. So our sales in each state that occur the most frequently down to states that have either no sales or little sales. And I'm going to order this in descending order. So when we run this, we're now looking at an aggregate on our base table and then grouping it by a column that was joined to that base table. We run it and we see that our top state is null. So that means that we have more sales more sales with records that don't match on the join table than we do with some of these other states that actually have valid join criteria. So New York has 560,000 total sales, but we have let's see, $2 million in total sales that didn't have a state ID that we could group this into. So this would be an example of us needing to look further into that data, because that null value means that table join didn't succeed. So this would be an example of something where we might want to investigate further. And we could recreate this entire query here and paste it under. And maybe we just want to see everything. We want to look at all of the information across this table. And we only want to look at the values that had a join fail. What we could do here is we could do where location dot state ID is null, because we know that if the join fails, the value of any of the values or any of the columns on that join table will be null. So if we run this, we'll return that same object that we were looking at before with all the sales and then all of the join information. You'll see that all of these are null. And now what we can do is we can actually go look here and see why it failed. So we have some customer zip codes here that appear valid. You know, I would think that we have a customer zip code of 94217 or 70267. But we could even validate that just by querying our other table. So we might say where the zip code on the US zips table is equal to 70267. And we'll see if this is even valid. And we get nothing returned. So it's kind of interesting that, you know, we're missing zip codes, but this would be an example of looking at how you've joined the tables and how you want to analyze the data going forward, and being able to diagnose where the join failed. Was it because of a data type error on your base table, like the toy sales table, or was it an error on the table we joined to? Maybe we have an entire dimensional row missing. This would be an example of that, where the row on that dimension table is missing. So the SQL engine has nothing to join it to. It doesn't know what to return because up to this point, it's just showing as unknown. But we could theoretically insert a row into the US zips table for this zip code. And then when we rejoin and rerun the query, it would succeed and then group it into the correct state. So that'd be an example of how you might use a left join to start exploring the data and exploring some of the aggregates and then fleshing out some of the details later. Why did the join fail? Where did the join fail? How can we resolve the problem? Things like that are going to be why you might want to use a left join over an inner join. And there's plenty of scenarios that you might run into where one join type makes sense over the other, or where you might have to ask a question, or you might have to answer a question that that warrants either eliminating rows that don't have a match or including all rows regardless of that match. Like in this example for toy sales, we might have to run a report for like accounting that says, here are all of the sales that took place for this particular year. And if they wanted to break that out by state, we could give them the information that we have for what state those sales took place in. We just have to notate that we have less matches, less joint or less matched rows than we do unmatched rows, which would signify that this isn't a good data model, or there needs to be some tweaks made to the tables before we do any more in-depth analysis. But that's a quick example of how we would do joins in SQL, inner and left join. So why don't we take a quick break? We've been going for just over an hour and 20. I could sure use a break. So we'll go ahead and take a 10-minute break, and let's be back by, let's do 12 minutes. We'll do 7:30. All right. All right. Hope everyone's back, ready for another hour of class. But before I go any further, does anyone have any questions on the joins that they might have thought about during the break that we could answer? If not, we could go ahead and keep on trucking through. Brenda, I think you might be on mute.
I had a question about, I didn't have a question so much on the join, but I did have a question about the quiz. I know one of the questions asked about alter table when they're asking about columns, but is there also a insert into for columns? So I guess I just had a confusion in that.
So insert into is going to be the syntax that you would use to insert a row into a table. I don't believe that there is a simplified query for adding a new column other than altering the table, because when you add a new column to a table, you're technically altering that table schema or how it's organized to include that new column. So you would need to use the alter table statement, and then you would have an add column statement after that to add the column. So we were looking for the alter table.
So when would insert into then be applicable?
If you wanted to insert a new row. So in the case of, I'll go back to MySQL. So in the case where we're looking at our sales by state, right? And we knew we had a lot of rows that didn't have a valid state ID. And when we went and investigated, we looked at one of the zip codes for a sale that didn't have a corresponding ID. What we could do is we could run an insert into statement. So insert into, and in this case, it'd be learn.us zips. And then we would define what all the columns are that we need to write to. So we would have like zip, latitude, longitude, city, state, so on, all the way down the row. And then in each of those values, or after we declare what all the columns are that we want to write into, that's when we would write values. And then in another parenthesis, all the values that we want to insert into. So that'd be a time where you'd want to use an insert statement, is if you want to add a value to a table where there's not one that already exists.
Got it. Thank you. I appreciate it.
Yep. Any other questions? All right. So now that we've practiced some inner and left joins and we've really gone over a lot of the basics that are important to know about joins, let's talk about unions. These are probably not as much fun as joins, if any of this is fun, I suppose. But what's the purpose of a union compared to a join? You can see by the Venn diagrams that I have above that there are two different types of unions and they behave differently. We have a union, and then we have union all. And what does a union do? It combines the results set from multiple queries. It could be 2 queries, it could be 5, it could be 100. There are a lot of cases where unions get used in a variety. Well, there's just a variety of ways that unions can be used. But it all boils down to creating 2 distinct data sets based on the criteria of a select statement, and then joining them together. And the difference between the union and the union all is that in a union statement, you might want to return all the distinct values from the 2 queries. That would be an example of when you'd use union so that you can eliminate any duplicates you might have. And then in a union all scenario, maybe you do want to return all of the values regardless of if there's a duplicate. And so you can see we have 2 tables here and we have 2 result sets. So I'll zoom in so that you guys can see these tables a little bit easier. But for the sake of the class, let's imagine we have 2 different tables. We have a customers table that stores information on those who are buying our products. And then we also have a suppliers table, which gives us information on who's giving us the products to sell to our customers. And if we wanted to query all of the cities that our business has a footprint in, whether that footprint is our customers buying our products or it's our suppliers that are giving us the products to sell, We just want to know all the distinct cities. That'd be an example of when we would want to use a union so that we can suppress anything that's duplicated. In this instance, if we were to union these two data sets together to return the city, which is the example we use on this slide, what we would do is we would create two independent SQL queries. One of them is going to be select city from the customers table, and then we'll write union underneath it. This is going to merge the two queries together into a single data set. And when we use union, it's going to suppress the duplicates for whatever column we're unioning against. In this case, it's city. And then after that union statement, we'll have another select statement, which is select star or select city from suppliers table. This can be shown right here, where we select the city from the customers, and then we union select city from suppliers. So we get all the cities on the customers table and all the cities on the suppliers table. And then once that entire group set has been computed, then we want to order it by the city name. And we can do this in ascending order or descending order. In this case, it's going to return everything in ascending order. So the results that we get are Ann Arbor, Berlin, London, Mexico, and New Orleans. So if we're looking at this compared to a union all, right? When we look at the data set, you'll see that we have 6 rows total. We have 1 row for Berlin. We have 2 rows for Mexico. We have 1 row for London. We have 1 row for New Orleans. And we have 1 row for Ann Arbor. So when we run that union statement, which is the one that suppresses those duplicates or only selects the distinct records from the tables that we queried, we would only return Mexico 1 time, and we would return Berlin, London, New Orleans, and Ann Arbor. If we did the union all, this just means I want to return every row from these 2 tables, even if there's duplicates. So if something shows up twice, we show 2 rows with the same value. And in this case, since we have Mexico showing up twice here, the result of our union all statement is going to show Ann Arbor, Berlin, London, Mexico, New Orleans. So not a whole lot to add onto there. Unions will be used for some specific use cases. There is an example. So an example of a time that I used a union statement before was when I was working at a travel nursing agency. And we had a table that showed every type of placement that occurred for like a travel contract. So each of these travel contracts hits multiple different users, multiple departments before that nurse maybe goes and works a travel contract. And each of those steps of the way, we would timestamp that particular contract saying, on this particular day, the traveler submitted their application to the hospital. And then on another day, the traveler got interviewed by that hospital. And then we would potentially have upwards of 10 or 15 rows for this one same contract that had timestamps for each of the different points in the deal's life cycle. And for some sales metrics, the sales managers only want to see activity at certain points of these contracts. They only want to see when the nurse submitted the application, when the nurse got interviewed for the application, when they got placed at the facility. So that would be when the nurse actually started working at the temporary hospital, and then when the day that they actually started work, when they started working and when they finished working. So we might have 10 or 15 different types of activities that occurred, but we only want to return information from that table for things like the submissions, the interviews, the placements, and then when they started working. So what we could do is we could actually create 4 different queries. We could select star from the table where the action type equals, say, like submitted. And that would be a query that returns only rows for contracts that had an application submitted. And then we might have another select statement, which is selecting everything from that same table where the action type is interviewed. And then we might have another one similar for like the placed, and then we'll have another one for those that worked. And each of those is going to have a different date associated with them. So what they would want to do is they'd assign points based on the day that each of these activities occurred. And so to create that same data set, it was either we selected everything from the table where the activity types were in those 4 particular activities, or we could separate these out into 4 more simplified queries and show how we're unioning them together or merging them into one data set. So we would have, in that case, 4 different queries where we'd select the columns we wanted and then union each of those examples together. And then at the end, we would have a data set that showed every one of the applicable activities for the sales managers or the recruiters, and it would count the amount of these records that occurred by date or by month or by quarter, and they could set their sales quotas based on that. But the engineering work that was associated with this particular project used unions instead of those select statements. Just another example of there not being one singular right answer to any of these questions, but there are multiple methods of getting to the same answer. We could use unions. We could only filter the table down to the records that have the attribution we're expecting. It's all up to personal preference. And then there are some cases where you might want to use a union, i.e. when you are working with 2 completely different data sets. You might have, if we go back to that previous example, we might have a table that only shows travelers that have been interviewed for a particular job. Call it traveler interviews. And then we might have another table that only stores contracts that have been that have started working. Call it working traveler. And we would union those 2 together, even though they're from 2 different databases or 2 different tables. We can select the data from each of those tables independently. And so long as they have the same columns, we can join them together and have one large data set with all the information in that or in those queries. So that's kind of a brief overview on unions. I know it's a little bit trickier than joins, but are there any questions on these?
Yes. So correct me if I'm wrong. Are unions a way to kind of get around having to write a subquery? Because the only time I've ever been introduced to subquery is when like you're trying to pull like 2 tables together with information and you don't want everything to like duplicate. So you pull like certain columns and join them together.
I don't know if I would use the example of a subquery with this. When I think of a subquery, I think of we might want to select something from a table where the results are in the result of another table. So an example that I'm thinking of is like, let's say we wanted to select all of our sales, and then we join to another table with like all of our zip codes.
Right.
And then we say only return records where the state ID is in, and then you have a list of all the states that you want. Maybe you create another query inside of that says select everything or select all of your states from the zip code table where the region is in the Southwest. Like that would be an example of using the subquery to return multiple values and use all of those values in your like result query. I don't know if I would consider that as like this as similar to a subquery, I guess. This is more for either merging 2 data sets together that have something in common or querying from different tables, different sources, a set of similar information that could technically be viewed in just one table or one view. So hopefully that helps.
Okay.
I had a question.
Sure.
Do you still have to use alias for when you do union?
Technically, no. If you're joining multiple tables to then union for another result, that'd be a case where you would want to alias it. But in the example here, where we're just selecting a column from from each of these tables, you don't have to alias these because each of the queries are treated independently. You only need to alias tables when you have references to multiple different entities. So think about when we look at like the join, for instance, we could select from different columns from each of those tables. And if we don't alias them, there's no easy way for the query engine to figure out what you're querying against. Because if we're joining two tables together, there's probably something that's similar about them, or there's some sort of similar attribution or information stored in those tables. And so when you like select something, if you don't define what table there is, and there is a column name in both of those tables with the same name, your query won't be able to run because the SQL engine won't know which column you're trying to refer to. It could be on your first table, it could be on your second table, or your third, fourth, so on and so forth. So those are going to be the times where you would want to alias your tables and columns. But in this case, for like these basic queries where we just want to union the result sets from two different queries, you wouldn't need to alias this because we won't run into those ambiguous columns where we have multiple columns of potentially the same name on different tables. So hopefully that helps.
Thanks.
Any other questions before I move on? All right. So we've talked about joins, we've talked about unions. Now let's build on top of that. So we know how to take different tables that have something in common and join them together to extract some form of analytical value. But once you start to add more tables onto a database and you start to understand the relationships, the more relationships you establish in a query will then start to accumulate into something called a data model. You probably hear about data models all the time. They're used in data science everywhere, and there's multiple ways of organizing data models and how they're joined. And there are different use cases between, like in this case, the examples were an OLTP database, an online transaction processor, and an OLAP, online analytical processor. OLTP databases, since they can have so much information and data needs to be retrieved quickly and efficiently, we want to reduce essentially data size, or the amount of data that we store in whatever we're storing our data in. So in this case, it could be a cloud database. Nowadays, storage isn't as important of a consideration for like OLAP, for example, because storage is really cheap. Most of the costs that get accrued on like a data science department or an analytics department are on the compute side, because it takes so much compute power to run queries against millions, tens of millions, potentially billions of rows. But OLTP databases, if we continue to store less data or refer to other tables, that's when we can start to offload a lot of the table size onto other like relational tables. So we'll get into some examples here in the next slides, but to give you an idea of the different modeling techniques that occur in business intelligence and data science and analytics, we have entity relation modeling, which is some of our simpler models that just display data entities, as they're called, and then relationships that they have to other entities. So these entities are generally tables, but they're to show that this is more conceptual in nature than it is practical or from an engineering standpoint. We just want to know how each of these items is supposed to relate to each other. And the idea of these entity relation models is to show a 10,000-foot overview of a process or a set of data, so that those who are non-technical, maybe like you and me, can't necessarily understand it as well. This helps them look at entities that they are probably familiar with and then think about how these might be stored logically or how we could describe them with other tables. That's when we start to get more into the relational modeling side, which is similar to entity relation diagrams, but each of those entities is a table, and those tables have properties and relationships, and we define them using programming techniques. So we'll define what the column name is going to be on the entity, and then what data type those columns are stored as. Is the data that we're working with an integer? Is it a string? Is it a true false value? These are all things that get denoted on a relational model. And it also shows how many entities can relate to another on a table. So we'll talk about one-to-one relationships and one-to-many relationships and even many-to-many relationships. But the other two database modeling techniques that we're also going to touch on are data flow modeling, which may be applicable to those who are in like higher positions within like an organization in tech especially, or are working in product design, where we just want to understand how data progresses through multiple systems or processes and how data is input and how it is output from a system. Because there may be multiple tasks or multiple processes that occur in one job, but we need to understand why some of these processes occur, how they occur, what data stores they touch, what data looks like when it's input into the system versus what data looks like when it's output of the system or when it reaches the end of a process. This is what data flow modeling is concerned with. And then the last one, which is kind of my bread and butter because I work in primarily business intelligence, is dimensional modeling, which is what like Power BI and Tableau are built to succeed on top of. So you may have heard this called star schema before. There's also snowflake schema. But data gets organized into two different types of tables. We have facts, or tables that contain our measurables. So think business processes, or like sales is a good example, or activities, transactions that occur. These are all things that are facts. We can measure them. We can count the number of sales that occur. We can sum the amount of revenue that occurs. We can sum the amount of miles that we ride. We can count the number of movies that get released by a particular year. That's an example of a fact table. And then we also have dimension tables. These dimension tables are going to be things that describe those events or those fact tables and measurables. So when we make our queries and we refer back to like the left join, the inner join, the right join, the full outer join, we're joining all of these dimension tables to the fact table so that when we measure our fact table, our total sales, our total revenue, our number of bike rides, our number of titles added to Netflix by year or whatever, we're going to write that function on top of the fact table and then use the information on our joined dimension tables to then describe or break out what happens for each of these facts or measurables. So think of solving some questions like how many sales occurred in the state of Nebraska, or how many rides occurred between May of 2022 and September of 2022, or show me our total sales by product type. These are examples of formulating a query using facts and dimensions and referencing a fact table for your measurable and a dimension for how you want to break out that particular measurable or how you want to analyze the metric that you've returned. So we'll get into each of these individually. What's an entity relation diagram or entity relation modeling? This is going to be the most simplistic diagram that you can make, and it's going to show you how each of these entities relates to another. So entities, think of an object, a subject, a process. These are all tables. They could be tables that are applicable to like a company department. These are things that you would put as an entity or a table, these boxes over here on this diagram. And then each of those entities is going to have an attribute. These attributes are columns. They describe an object. They describe the subject. They describe the entity. So you can think about the 5 W's. These are great ways of engineering how you might store information on a dimension table. When we think about products, there's things that we might want to know about that product, like what was its color? When did we start selling the product? Maybe even a why. Why did we stop selling this product? It could be like a cancellation reason, or trying to think of the term, like a product deprecated reason. Or we could maybe ask what stores is it sold at? These are all things that could be stored on a dimension table in an attribute. It describes something that you're trying to measure. And then there's relationships. These are how we put all of these tables together. So the relationships will eventually translate into an inner join or a left join. So when you read from these entity relation diagrams, if we wanted to query from one of these tables, it would be select star from either teachers or subjects or marks or students or groups. And then the joins would be from one table to the other, so on and so forth. So selecting columns from each of these tables, joined on the criteria outlined here. And in this case, we'll talk about the one-to-one, one-to-many relationship types. But the way that you can describe this is thinking about a class. If we start at students, right? One student defined by the student ID column could have one too many, so more than one marks. And this is just a different name for like grade, right? So a student could have one or many grades. And I'm not going to touch on optional, which is the circle down here, which is optional 1 or optional none. But in this case, what this entity relation diagram is saying is that a student isn't going to be a part, or isn't really going to exist unless they have a mark or like a grade in this grades table. And this is going to define kind of the rules that you have for like table design. And you have to think about this kind of logically because in many places, especially new companies, or even organizations that are trying to start up, a lot of this isn't going to be known right off the bat. So you have to take a step back and think about all of the different areas that could be applicable to the thing you're trying to measure, the things you're trying to store. And you have to think about what defines like one entity. So for students, for example, what defines a student? Can a student be enrolled in a class, or can a student exist not enrolled in a class yet? It could be like an enrollee. Or in this case, if a student can only have a record on the students table if they have a grade for at least one assignment, that might not be valid for like an application. From an application design perspective, we may have students enroll or say they're going to take a class, but then never take the class. They could still be considered like a user or a student or a person. So there's a lot of ways that you'll have to model data out that aren't already done for you. So sometimes it's just using a little bit of creativity or adding a little bit of knowledge, because there's in a lot of companies, there are good resources that will tell you like how they've structured some of their processes. And you'll always want to use terminology like, in this case, how do you define a student? Can a student have grades before they're entered into the student database? Can a student exist without being enrolled in a class? Can a class exist without having a teacher assigned to it? Can like a class subject exist in the subjects table if there's no classes that are being taught of that subject? So that's what a lot of these lines are doing. They're establishing some of those rules for how many records can we have on another table that relate to the other table. These are all built on top of like the concepts of joins. But the relationships, when we talk about these, what are one-to-one? What are one-to-many? What are many-to-many relationships? A one-to-one relationship means that one row on a table can only correspond to one row on another table. So a common example of this is when we're looking at like a sales table, for instance, and we have tens of millions or maybe even hundreds of millions of sales tables. And there's a ton of attributes that are only relevant to that particular sale. I'm thinking about things like value chain dates. So what date did the sale occur on our POS system? And then what date did that order make it to like the warehouse to fulfill an order? And then what date did that order get shipped out? What date did the customer receive the order? What date did the customer review the order? So you can see how there's tons of different data points that we might want to analyze on this one particular entity. But we can't store that all on like a fact table in business intelligence, because those tables, the wider they grow and the taller they get, so the more columns we have and the more rows we have, the more difficult it becomes for the OLAP cube or the processor in the background to make that computation. It could take minutes. It could take 1 minute. It could take 10 minutes. It could take an hour, depending on the size of your table. And so you may want to offload a lot of this data onto another table. Call it sale details. And you'll join that table, and each of those sale records, which is the distinct value on your original table, may have all of these dates and attributes on a similar table, but we can make that table as wide as we want because we're only going to look at one column on the relational table that we join to. So it improves performance, and we know that we're only going to have one record on that join table for every record that's on our base table. So this would be an example of a time where we would use a one-to-many. An example of when we would use a one-to-many relationship is if we have multiple records on a single table. So think about our fact table or what we want to measure, right? We may sell multiple of the same product. So think about like if we're looking at the toy sales table in our database, we might only sell 5 or 6 different products. But those 5 or 6 different products might have a lot of different attributes that describe that particular product. Think about the 5 W's. What color is the product? What shape is the product? How old is this particular product? How long have we been selling it? Tons of different questions that we can ask of that particular dimension with the 5 W's. That'd be an example of having maybe tens of millions or hundreds of millions of sales for just these 5 or 6 products. But it doesn't make sense to add another column for 10 million rows that shows what color the product is. It's easier to just store one record on a corresponding table for that particular product that shows all of the descriptive attributes of that particular entity. So like for a product, for example, we might have 15 or 20 different attributes that describe the product that we know about, that a subject matter expert like a product officer may know right off the top of their head. But we might want to analyze that later on down the road. And so it's easier to use the dimension to filter the results on your analysis than it is to add another column onto a table. When we talk about like the OLTP databases, for instance, those tables can grow rather large, and our easiest optimization is to prevent the tables from becoming too large from a data size perspective. So it's easier for us to correspond any of this data to the dimension instead, because it reduces our total data redundancy. We don't have columns that have multiple of the same values. So this is where some of the optimization techniques will start to show their head. And then the last one is a many-to-many relationship, which means many rows can be associated with many rows on another table. And this is a much more complex scenario to outline. The thing I will point out is that many-to-many relationships are not ideal for OLAP cubes or analytical cubes, because in order to properly filter like your facts from your dimensions, if there is a many-to-many, is by using what's called a bridge table. And that bridge table is saying, yes, I know there's a many-to-many relationship, but I need to know how to interpret this fact or measurable table based on the values that are actually in this other table. Think of it like a midway point between what you're selecting to analyze by and the actual metric itself. I don't have a good example off of the top of my head. However, this source right here from Lucidchart will tell you a lot of the things you need to know about ER diagrams. And I think it even gives you some examples of like when practically many-to-many relationships can be used. But the relationships that you will primarily see in like data analyst and business intelligence is going to be one-to-one and one-to-many relationships. So as long as you know those two, you should be okay. The next one, we'll talk about relational modeling real quick because this one's a bit easier to explain. It's roughly the same thing as the entity relation model. However, it integrates a technical physical layer on top of that, and it will tell you what kind of data type you're using, the exact schema name for the table. So this just adds an additional layer onto your entity relation diagram that shows like a database architect or a database administrator how you want your environment to be set up. So that's the advantage of a relational model over just a simple entity relation diagram. The next one that I wanted to talk about tonight is the data flow modeling, which this is done quite frequently by analysts and engineers alike. And this is incredibly helpful to illustrate how data comes into a system and how it comes out of a system. What happens to it along the way, what different parts of your database are manipulated, touched, altered in a particular process. So this is just describing that flow of data through the system or the process. We can model these processes that are performed on data. We can talk about where the data stores are, which is where that data gets held, and then the people, the systems, anything in between that actually interact with that data. And it's incredibly useful for identifying areas of inefficiency or just communicating design requirements. There are multiple ways that data flow modeling can be used practically in businesses and organizations everywhere. Just looking at this example for sales, this diagram right here is describing what happens when one item is sold. We touch so many different tables, and there are many different facts, dimensions that get manipulated along the way. So when we analyze this from left to right, what happens is the customer, or it would be a record on a customer table, initiates a sales order. After that sales order is submitted by the customer, that's when someone comes in and approves the sales. And the only way that sale can be approved is if that customer has a valid credit record. So the customer's sale gets approved, and then there's an automated process that kicks off to look at that customer's credit record. And then there's two ways that sale approval could go. It could either be approved and sent to the customer for billing, and then that bill goes to the customer, and we post the bill to our accounts receivable to collect down the road. And then the stock also gets released. So this is when the warehouse knows to ship the good, which is the process right here. When that item gets shipped, we then write the shipment to our shipping log table, and then that item also gets a packing slip and goes to the carrier. And we know what the carrier's name is. We know a lot of information about them, and we know that this particular order is being fulfilled by this carrier. And then when it gets shipped, we give a shipping notice to the customer that we billed to, and then we generate a sales order. After that information is posted in billing, accounts receivable can then prepare the invoice, and it goes to the accounts receivable records. So this is just an example of how business processes get modeled out with a data flow diagram. And so you can see every point of that particular process, all the tables that we're writing to and manipulating along the way. And if there is something that sticks out as being like inefficient, or we want to make an improvement to the system, this is probably going to be the first place that a lot of those decision makers go to. They want to see how logically on this diagram we're going to improve the system. Can we justify the expense for the improvement? Things like that. So that's what data flow modeling is primarily working with. And then the last one, which is dimensional modeling. This is used frequently in data warehousing and business intelligence to optimize our data for queries and analysis. So you've probably wondered over the last few days, or maybe the last few classes, why I modeled the tables in our databases the way that I did. And that's primarily so that we can show it in a easy to understand, easy to query, easy to analyze format. We have things that we want to query against or measure, which are going to be things like the biking table and the toy sales data or the Netflix titles. And then we can slice all of that data by a couple of different dimensions, like our US zips codes and our calendar table, our dates. Date time intersections are very frequently used in dimensional modeling, and we can further break out a lot of that information, or all of that location information, on a completely separate table. So when we format these tables for analysis, we create what's called a star schema primarily. And that star schema means that all of our measurables are on one table, and then anything that describes that measurable, whether it's on 5 tables or 10 tables, all of them will have a key that corresponds to that middle table. And what we want to do is optimize that middle table, this fact table right here, to be as efficient as we possibly can. So some considerations that we have to make are data size. So only having columns that are applicable to the measurement and not applicable to a dimension. So this would be things like value chain dates. So if we have multiple dates associated with a sale, we might offload that onto a completely different table, like a sale detail table. If we have a product, we don't want to list product information or product attributes on the sale because it could be redundant. So we put it on a sale or like a product dimension. And we try to reduce that measurable table down to only the keys, and then apply aggregates based on the values in these other joined dimension tables. So it allows us to do what's called multi-dimensional modeling, which means that we can aggregate a fact. So if we look at sales, we might want to sum the total of revenue, or sum the total of items sold, or count the number of orders that occurred, and then slice it by things like maybe we want to see all the sales that occurred in a particular store between 2 dates. That'd be an example of creating a multidimensional query, because we have to query all of our sales based on the store dimensions attributes and the time dimensions attributes. Or if we wanted to quantify our sales by customer and by product that they purchased, we would use attributes from the customer dimension and the product dimension. So now that we've talked about all of that, why would we want to use dimensional modeling? What's my sell to you to implement a star schema or a dimensional model in your organization, or even in the way that you organize your data? First and foremost, it is the easiest and most straightforward data model to understand. It allows you to organize entities based on their real world meaning. You don't have to worry about there being multiple tables that describe, or maybe just multiple chaining tables is what I'm trying to get at, that you might miss in just a simple one table to one table join. It also increases your query speed and simplicity by quite a bit, because some data models can get very complex where a joined table also has entities stored on another joined table. And then there's attributes that describe those entities even further. So it can start to grow out of control pretty quickly. The dimensional modeling technique is much easier to understand and communicate to stakeholders. So I try to model most of my data in a star schema format, especially because it is easiest for software like Power BI and Tableau to interpret and then run calculations across. But that's not to say that it's perfect. There are certainly some cons. You can imagine that when we have a lot of tables that get really large and we have a ton of dimensionality, we start to get some redundancy in our facts eventually. And this leads to a larger amount of storage that we use in our OLAP cube. Kind of like I said before, this isn't as big of a concern anymore because in the data world, data storage has become incredibly cheap. So we can generate large amounts of data for next to no money. It just costs a lot to be able to query a lot of data. The more, trying to think of a better way to describe this. The larger the size of the data is in terms of sheer rows and attributes that we describe those rows with, the larger in like data size it becomes. And if we're only trying to run an aggregate on top of like a sales fact table with one other attribute, it's okay if we have some redundant data in the fact, so long as it only corresponds to a store dimension or not a store dimension, just a dimension table in general. So those are the four major data modeling techniques that are out there. Any questions on these four that we just went over, whether it's ER diagrams, relational models, data flows, or dimensional models? All right. So how can you actually create these models? There's a ton of software out there that you can use. My recommendation is to use the free one because it provides you with the most options and the most versatility in your artistry compared to some of the other options that are paid. You've probably heard of Microsoft Visio before. It is an almost identical platform to Draw.io. However, you have to have a license for it. So it makes more sense to use Draw.io instead. But there are other pieces of software that you can use. If you just look up database modeling software or entity relation diagramming software, you'll find a number of different options out there that you can use. Some of the examples that I put down here are Lucidchart, Google Drawings, Smart Draw, Open Office Draw. There's a ton of options, and really it's just your pick of the flavor. You can have chocolate ice cream if you want, or you can have strawberry ice cream. They will both satisfy you nearly identically. Just depends on your personal taste. So what did we cover tonight? We're almost to the end of class. We learned how to apply SQL joins again today. We further covered what they are, what they're used for, how they can be useful, and how to use them. We also learned about all the database modeling techniques that there are, or at least a small subset of them, the most important ones, as I like to cover. And then we also learned about OLAP and OLTP database types, what their differences are, the cases where you might want to use one over the other. So that's just a short list of the things that we covered tonight. And now that we've covered it all, let's talk about the homework. We have a situation, we have a task, and then we have some requirements. So let's just assume that you've been hired by a startup company that sells educational software. And just by a coincidence, they teach SQL classes. Your first task on the job is to create an entity relation diagram in Draw.io of a grading system, or even just a class system in general. I've already created the framework, so you have all of the entities that we might want to use in this example. All you have to do is tie these entities together. Show me how this might logically be modeled. You'll want to create one-to-one, one-to-many, or many-to-many relationships in the file where necessary, and then identify what the primary keys on the table are and what the foreign keys on the columns are. The primary keys you'll want to identify with a PK on the suffix of the column name, and foreign keys you'll want to correspond with an FK on that column on the join table. And I've already got a file put together for you, so I will actually show you how to import this and then make some updates to it and give you kind of an idea of where I want you to go with this assignment. And this will be due on next Monday. So if you have makeup homework assignments, those are due by Friday at midnight. So if you still have one, please try and get that done before Friday at midnight. And then today's homework will be due before we start class next Monday. Actually, I changed my mind. It'll be due on or at midnight after class on Monday. So you can turn it in before class or you can turn it in after class. You should still have a few hours to do that. And then for our next class, we're going to talk about data storage, management, and administration, data governance and data quality, and then a little bit more about data warehousing and business intelligence. So from the beginning of class, we talked about some of the more basic concepts like how to extract data out of a database, how to provide value with the data that we query. And then we started figuring out how to add more tables to a database, and then how to join these database tables together. And then how all of these database joins create a data model that we can then query and do multidimensional analysis on. Now that we've learned how to do that, we're going to talk about how to manage this data, how to administer it, how to store it, how to make sure that the data you're writing to these tables is correct and accurate, how to make sure that business policies are written around the ways that you've structured your database rules. And then most importantly, how we're going to dole all of this information and all of the metrics that we've compiled from this data model into something that the business can use. So that's it. That's class for tonight. Are there any questions before I get into the homework demo? All right. So for the homework demo, what you're going to want to do is actually go to draw.io, and it's you can also go to app.diagrams.net, and I'm going to send you all a file for tonight's homework. So I'm going to post that into the Slack channel right now. All right, class 4 homework. There we go. Okay, so you'll want to download that draw.io file that I just linked. So when you hover over the code preview, you'll get like a cloud icon that says download. It should go right into your downloads folder. After you do that, as you can see, it's here in my downloads folder. You'll want to save diagrams to device, and you'll want to open an existing diagram. So this is where you're actually going to go in to the file location. So in this case, since it's in the downloads, I'm just going to pull this in, and it's going to open up the file that I've just created for you guys before class started. It has all of our entities. So these are all tables, and these are all the attributes of that particular table. And now what we need to do is we need to drag all of these different relationship types between each of these tables. So to get you started out with, we'll start with the most basic of all of these, which is our classes table. And when we think about classes, we have actually, no, let's not do classes. Let's do homework, because homework is pretty close to like a fact table. We have some attributes that describe that particular homework assignment. We have an ID, so something that makes each of these homework assignments unique. And each of these homework assignments will be part of a class. And then of all of these homework assignments per class, there might be multiple students. So we need to know what student completed what homework assignment. And then we might also want to know what date the homework was assigned, what date the homework was completed, and then what percent that student got on the homework. So now we need to diagram this out. So we'll start with homework, and I will want to save changes. You'll want to define what your primary keys are and what your foreign keys are. So in this case, the primary key, or what makes this table unique, what makes every row distinct, is going to be our homework ID, because the homework ID should essentially define what each of these homework assignments is. So I'm going to denote that this particular attribute is the primary key of the table. It should be unique. And then we have a couple foreign keys. So class ID is an example of a foreign key, which is going to relate to another one of our entities that we've been working on, or that we have up here. And then we also have the student ID. This is also going to be a foreign key, because we can describe the homework that gets completed by the student that completes it. So that's another example of a foreign key. Now, when we figure out what tables these need to be related to, now we want to think about where class IDs might be stored. I would think that those will be stored on the classes table. So we'll bring the classes table down, and now we need to create a relationship between the two. And this is where we start to get into some of the more complex questioning, like can the same homework assignment completed by a student be assigned to multiple different classes? And if not, then that's probably a one relationship. So there can only be one homework assignment, or one homework assignment per student per class. But each of these classes could have multiple homework assignments. So that means that one class could have more than one piece of homework, which is totally logical. There could be 5, there could be 10, there could be 20 homework assignments for a particular class. So when we model this out, we're going to use the one-to-many relationship. And when we establish this, we want to know that there's potentially multiple homework assignments for every class, but one homework assignment can only correspond to one class. So that means that we want to flip these. So I'm going to show you how to change these arrows right here so that it goes in the opposite direction. Actually, I'm just going to move this to the other side. Well, you could move it to the other side. If you wanted to change the type of relationship that's shown here, after you copy and paste the object down to work with it, you can use these line arrows right here. These two that you can see right here are the start and the end for the relationship cardinality is what it's called. We can switch these to show that the left side needs to be a many relationship and the right side needs to be a one relationship. And then we'll take these relationships and drag them to each of the columns. So since this foreign key, the class ID, corresponds to the class ID on the classes table, we can drag those there. And when we read this in an entity relation diagram, we would know that one class could have one or many homework assignments, but the one homework assignment can only be associated with one class. So you can think about reading it from either table to table based on the relationship or the cardinality that we give it. So from wherever the line originates is where you declare like how many of one entity can exist on another table. And on the other side is it's essentially the inverse direction. But this is how you would want to continue to create this entity relation diagram. And all of these tables are going to correspond to another table. And so what I want you to be able to do is put all of these tables together and then figure out what relationships can be used between each of these tables. So we've already done the first one as an example, but technically that is the end of class. That should hopefully get you enough to continue on the homework by yourselves. But I will stay online and help you guys along with the homework if you'd like it. Otherwise, that's it for class tonight. If you want to stick around and talk about homework or there's anything else that you have questions on, please go ahead and stick around. Otherwise, you guys are free to leave. That is tonight's class.
Thank you.